In this video, let me show you how to do the calculations. Okay. Now, concept 0 is that the velocity is going to be, since we did a half circumference, right? The velocity is pi times the radius over half the period, right? Now look, if we put the 2 on the top, you get 2 pi r over t. But we didn't measure the whole period. We measured the half of the period, right? So the times that we get from looking at this, that'll be half the period. Pi times the radius over half the period will give us our velocity, okay? Now, to get our radiuses, let's look at this value over here. So we got to figure out what R1 is, right? R1 is these guys, right? We're going to use these guys to find radius 1, right? So you want to average those. Let's average those numbers right there. Okay, so R1 equals, so we'll do the average of this, right? So we're going to add, we're going to go 0.9481, right? That's that first one, plus 0.9680, plus 0.9632, plus 0.9775, plus 0.9639 are those things, right? If I average those, I get, when I add them, I get 4 point, and then if I divide by 5, I get 0.96414. So I'll say 0.964, okay? And that's meters, right? Then the question is, what is it plus or minus? Well, it's always going to be plus or minus the highest minus the lowest over 2, okay? So delta R is that, right? The highest R. So here is our highest R right there. That's the highest. And the lowest R is that guy right there. So I'm going to go 0.9841 minus 0.9632. And then I'm going to divide that by 2. And I get that it's plus or minus 0.010, I'll say. Okay, it's 0.45. Okay, it's 0.01045. But we only need 2 digits there, right? This is the thousandths place. That's the thousandths place. So that is our first radius. So let's look at our second radius here just for kicks. Okay. Our second radius is, well, we got to average those numbers there, right? So 0.5439 plus 0.5459 plus 0.5410 plus 0.5398. I'm going to divide that by 5. And I get 0.43. That can't be correct. Okay, let me check it. Okay, 5398. I got that one in there. 54. Oh, okay. I forgot the 5411. Okay. Plus 0.5411. Okay. I skipped one. Okay, so I get 2.7117 divided by 5. And I've got 0.542. Okay, so R2 is 0.542 meters, right? And now let's figure out which one's the highest, which one's the lowest, right? So the lowest is got to be the 5398, right? That's our lowest. And our highest is 5459. I think so, right? That's our highest. 5459. Yes. And that's my lowest, right? Okay, so I'm going to go 0.5459. This guy right here, right? That's my highest. Subtract my lowest, 0.5398. Divide that by 2. And this is 0.003. So this is plus or minus. And it's 0.00305. So I'll say plus or minus 0.003. And that's it. I just have to say 3, I guess, huh? Okay. So because we've got like a thousandth place. And that's really all we really... I mean, really, we can't really measure a millimeter using this, right? Okay, so I'm carrying extra sig figs here, right? And then let's look at the periods. We can figure out the periods as well, okay? So my period here, T1, is going to be, well, half of T1, right? Half of T1 is 2.002 minus 1.535. Right, so what is that? 2.002 minus 1.535. That is 0.467. Now, what's the uncertainty of that? Well, take a look at this, right? Notice how there's some smear on there, right? Did we really catch it at the edge? Or did we catch it a frame early or a frame late? So the uncertainty basically is the time between frames. That is 1/30th of a second, right? So all of our delta t's are basically a 30th of a second, right? A 30th of a second is plus or minus 0.033. There's a lot more threes, but I just didn't show them. Okay, so that is T1. Half of T2, remember we're only dealing with half periods here because it only went from one side to the other. Half of T2 are these times here. Okay, so that's going to be 2.602 minus 2.468. And that is, what is that? 2.602 minus 2.468. And that is 0.134. And that is also plus or minus 0.033 seconds. Okay, so now we've got a data table, right? Your data table is going to be a lot nicer than this, but basically you need the two R's and their uncertainties, the two times and their uncertainties, right? Now, let's calculate, now we have to calculate the velocities, and we have to calculate their uncertainties, right? Okay, so V1, let's calculate that here. That's just going to be pi r over half of the period, right? V1 is pi r1 over half of the period, right? Okay, are we ready for this? So it's going to be pi times 0.964, and then half of the period, the first period is 0.467. Okay, so let's do this. Pi times 0.964 divided by 0.467. And I get 6.485. And I'm content to just leave it at 6.485. 4 sig figs, right? I don't know. I really don't know. Okay. And then let's figure out the uncertainty of that. Okay, so the uncertainty, we're going to use this basic idea, right? The uncertainty of a velocity is to the velocity, as the uncertainty of radius is to the radius, plus the uncertainty of time is to the time. Now, I'm just saying that pi is probably not too uncertain, okay? So let's set that up, right? The uncertainty of V1 is to 6.485, as the uncertainty of the distance, which is 0.01, is to the distance. And then the uncertainty of r of the time, right, is 0.033, and the time was 0.467. So now we solve for delta V1. Remember, the way to do that is to take the 6.485, multiply by this, right? So I'm going to use all the digits on my calculator. I'm just going to go times left parenthesis 0.01 divided by 0.964 plus 0.033 divided by 0.467, right parenthesis, and I get plus or minus 0.5. So delta V equals 0.5. It's actually 0.53 meters per second, right? So this would be plus or minus 0.53. So it could be as big as almost as 7. Right? It could be as small as a little less than 6. That's the range of this thing, right? Okay. All right. So let's, obviously you can stop the video here, but I'm going to continue on. Let's figure out V2 because I'm just damn curious, right? Okay. So V2 is going to be pi R2 over half of T2, right? So that's going to be pi, and then R2 is 0.542. Over half of 0.134. All right. Yeah. Okay, so let's do that. Pi, second pi, times 0.542 divided by 0.134. Oh, wait. It's not half of that, sorry. That's why I was daydreaming, right? This is half of the t already. Okay, sorry. Okay, don't put the half in there. Okay. Okay, are we ready for this? Ooh, 12.7. That's 12.7. Now notice it's more than this, right? In fact, it's nearly twice that, right? Okay, but we still haven't figured out the uncertainty. It could be that I'll say it's 707 meters per second, right? It could be, though, that if the uncertainty of this is like 6, then we really haven't shown that it couldn't be a constant velocity. So let's figure out the uncertainty of this guy. So the uncertainty of V2 over, it's not looking good, though, for the constant velocity model, right? 707 equals, okay, so let's go pi times, what am I doing? Dear Lord. I'm just daydreaming. Is there an eraser? There's not an eraser. Okay. Ignore what this guy's doing here. Okay. So that's going to equal, and then this uncertainty is, for this distance, is 0.003 over 0.542. Sorry, I'm just a little spacey here. And then our time, it's the uncertainty of this time is 0.033 divided by 0.134. Now, I expect this uncertainty to be bigger because the uncertainty of time is the same, but this time is much smaller, right? So this will be a bigger fractional uncertainty. So take this number again, the 12.707, and go times, left parenthesis, 0.003 divided by 0.542 plus 0.033 divided by 0.134, right parenthesis. And it's pretty big. This is plus or minus 3.2 meters per second. It's 3.199, so I'm just going to say 3.2, right? So this could be as big as, it's plus or minus 3.2 meters per second. Okay? Now, we need to make an argument here, right? So in your conclusion, you need to say, the velocity before was this, and the uncertainty was this, and the velocity after was this, and the uncertainty was this. Yeah, the velocity after was more, and even taking into account, right, if I subtract that, right, if I go 12.7 minus the 3.19, that brings it down to 9.51, and we could bring this one up to about 7, but these are irreconcilable. There's no way that these could overlap. The fact that they don't overlap means that you have just disproven the constant velocity, right? Now, if they do overlap, you have failed to disprove the constant velocity, right? It still could be true if they overlap, okay? All right, I think I'm just going to stop talking. It's not going to get better after this. Okay, grasshopper walks into a bar.